All right, it's 9:30, so I'm going to get started. Hope everybody's having a. Oh, come on! I just started talking, and my internet connection's now unstable. I hope everybody's having a good day. You can see the end in sight of a lot of things, and then what I'm talking about, I guess, is this course because we're under 2 weeks now, aren't we? Final exam will be what, 2.5 weeks from now, less than 2 weeks left of class time, so you can count them on down. Getting a little short of time here as we move towards the end of the semester, so that's a good thing because that means there's only so much more to do before we put a bow on it and move on to the next adventure in life. All right, so I want to do three things today. We're going to start off. I have a video I want to show you about these eddy currents that I was talking about on Wednesday, because I suspect a lot of you have never come into contact with it unless some very good high school teacher showed you the effect I'm talking about. If we were in the campus in La Trenta lecture hall, I would absolutely have brought this demonstration down and showed it to you there. I want to talk about some new material today. We're going to talk about self-inductance. Self-inductance is a way that we create another device. Mutual inductance is how transformers work. Self-inductance is what causes currents not to change instantaneously in a loop. So we'll talk a little bit about that. We'll continue that on Monday. And then last thing, I want to do some more of these Faraday's law, Lenz's law problems. I've got a PowerPoint. We'll go through it and we'll use the iClicker so that you can demonstrate that you're getting it, that you're seeing how the current's going to be induced due to an electromotive force which is induced due to a magnetic field, I'm sorry, an electric field that's induced because of a change in a magnetic field, which is what Faraday's law is all about. And so that's the plan today. The last thing we'll do is the clicker stuff. You can log in. I've set up the class whenever you want. Somebody asked me if I would post that PowerPoint set with all the questions that we're doing in iClicker, and I will once we're done with it, probably today. I have to annotate it with answers. Right now it doesn't have answers in it. They're all up in my head, I guess, and so I'll put some answers up and I'll show you an annotated PowerPoint I'll post in Canvas, and so you can practice on your own if you want. I'll put the correct answer like down in the bottom corner so you can hide it for yourself. All right, so let me start off by sharing my PowerPoint with you. And this is a little bit of just review before I queue up a video. I'm hoping you'll see the video on Zoom. It is my hope. Let's see. Did I share? Yeah, okay, I'm sharing. And let's go big screen. Hey, Justin, can you tell me you can see the PowerPoint? I had issues with this on
Yeah, I
Wednesday.
can see it.
You're good to go? All right, well, it probably just went blank there. All right, excellent. Thank you. And we'll make that minimized. And we're talking about these eddy currents. And the point, I guess, is as a piece of metal right here that isn't seeing a magnetic field goes to a region where there is a magnetic field, you might think of this like a big horseshoe magnet with two poles. You'll see that in a video here in a second. That could be what's creating this magnetic field right here. As the piece of metal goes from no magnetic field to a magnetic field, an electric field is actually generated, which causes an electromotive force, which makes currents swirl around. And then that current interacts with the magnetic field to give you what I would call a retarding, a slowing down force. And you'll see that very graphically here in a second, okay? I do want to make a point that I forgot to make on Wednesday about these electric fields that are induced, which cause electromotive force voltages, which cause currents because charges get pushed around in the metal in circles, okay? And if you remember, when we talked about electromotive force, we said it's just an electric field with a displacement. And truthfully, I don't remember if back there we called the displacement S or L. I'm calling it L now, but it may have been S back then. I've forgotten. And if you remember when we defined electromotive force, we said, well, we go from point A to point B, and you even had an exam question on the midterm where you had to find the potential difference between 2 points in space by, I guess, finding the potential at point B, finding the potential at point A, and subtracting them. But one of the points we made back there is if the final point circled all the way down, and so like there's a positive charge, and if you started right there at point A and you went around some path, it doesn't matter what the path is, but if you finished at point A, we said that the work you did the net change in potential energy, the net change in potential difference, which is just potential energy divided by charge, we said was equal to 0 when the cause of the electric field, and there's like my electric field over in that region where I'm moving around radially outward, we said was 0. But now if you look at Faraday's law, and we're talking about an electromotive force, an EMF, a voltage, they're the same, right? They're synonyms, kind of a misnomered synonym to call it a force, but it's still there. People do that. Now we're saying, hey, these electric fields go around in closed loops. And so the question is, why isn't it 0? And the answer is because that's the way nature made it. Apparently, we said words like when the electric field, great, Comcast, thank you, becomes stable. Hopefully you can still hear me even if the video goes bad, or vice versa. You can still see the video if the audio goes bad. Apparently electric fields caused by charges, because as you go around a closed loop from A back to A, you get 0. We say words like, yeah, that electric field is conservative. Energy is conserved. That's an R. Conservative. I'll stop writing right there because I'm writing with my mouse. On the other hand, though, this electric field integrated around a closed path, and that's what that means right there. You're taking some path from A back to A. You come back to where you started from. It's not 0. It's the rate of change of the magnetic flux, which means some magnetic field is changing. And that creates an electric field. But apparently, since this is not 0, this type of electric field is non-conservative. So there's a fundamental difference in nature between fields which are created from stationary charges. Those are conservative, and when electric fields are created from changing magnetic fluxes, changing magnetic fields, those are non-conservative fields. And that's, I guess, the big point I had to make. All right, and so we're talking about these circulating. If I change this magnetic field between, say, a north and a south pole on, say, a horseshoe magnet, I would cause an electric field. So even if there's no charges there, the field still gets created. If we put a piece of metal with free charges, those charges will cycle around. And that's this point of eddy currents. I think I want to stop right there, unshare this. Unshare this. Of course, that's in my way. Go figure. Put that over there. Hopefully it'll stop. And I'm going to go over to a quick little video I want to share with you that is on YouTube. I got to give credit to the guy who created it. And so let's share that with you. He's a professor at Duke University, and no, I'm sorry, Purdue University. You'll see his credit here in just a second. And hopefully you're seeing YouTube, and we'll start the video here. And I'll keep talking over it.
Another demonstration, eddy currents and the resulting magnetic braking that will occur on pendulum. So what I have here are two magnets. Okay, so this is like the north pole here, of this magnet, and the south pole here, this magnet. So there's a fairly uniform field in between here, and these are actually fairly strong magnets. So if I actually put a piece of steel in here, if it's a piece of steel, it would stick, and I probably wouldn't be strong enough to pull it apart. So what I have here is a piece of aluminum. Okay, so aluminum is paramagnetic, so it is only weakly magnetized, so it's not really attracted to the magnets. Okay, so I also have two other pendulums. Okay, this one has slots in it, and this one, the slots go all the way to the bottom, so there's no connection along the bottom. These I put in here will freely swing. Okay, so now it's...
Could you turn the volume up on the video a little bit?
Yeah, I can try. Yeah.
This one through the magnetic field.
Let's try this.
You notice how it breaks and stops. Now, if I did the one with the slots, we see it also breaks and stops, not quite as quickly. And finally, the ones with the grooves, so that there's no connection on the bottom, swings freely. Okay, what is happening is that as this one is swinging into the field, you have a changing magnetic field in this region. So that sets up a resulting current such that the magnetic field generated by the current opposes the increase in magnetic field. So that will be a field in the opposite direction, and that is what's causing the breaking. Whereas in this one, where we have these grooves, you can't get the circulating eddy currents because of the disconnection between these regions of the metal, and that's why you don't set up those strong induced magnetic field currents and resulting magnetic fields. Let's see if I can further clarify the eddy currents that will start to occur and the resulting magnetic field due to those eddy currents. So let's say we're sitting in that gap between those two magnetic poles, and we're looking, say, from the north to the south pole. So this circle signifies the area of one of the poles, and these X's signify that the magnetic flux density is into the page. Okay, so the aluminum pendulum now is trying to slide in like this. Okay, so as the aluminum pendulum is going in, what we see is that in this area, we have an increasing magnetic field inside the aluminum into the page. So that we know is going to induce a current, so that that induced current generates a magnetic field that opposes the increasing field into our aluminum here. So that will be a counterclockwise circulating currents are going to start to set up here. So that's going to generate a magnetic field that's coming out of the page and opposing the increasing field into the page due to the aluminum sliding into the field. Now, when the pendulum with the slots slides into the magnetic field area, these eddy currents cannot flow because now you have discontinuities, you have the high resistance air gaps, so you're not going to get those eddy currents and the resulting same large opposing magnetic field. So the kinetic energy of this pendulum as it's sliding in is converted to heat in the aluminum due to the eddy currents.
All right. We'll stop sharing that. And I think the important point there that people see that the first time and they go, oh, the metal just got attracted to the magnet. And that would be true perhaps if the pendulum was made out of a ferromagnetic material like steel. You'd come swinging through and, you know, it's a magnetic material. The two magnets would just kind of attract each other. But this is a piece of aluminum, which is not magnetic. If you took you touched the magnet to the piece of aluminum, there was no force there, okay? It was only when there was motion of the aluminum through the magnetic field that Faraday's law required a current to be set up, and then that current interacted with the existing magnetic field and caused the pendulum to stop. All right, that's any questions on that? I wish I could show you that, let you play with it, let you run the thing through. It's pretty dramatic. It's amazing how fast that aluminum pendulum stops as soon as it hits the magnetic field. So let's go back to sharing my PowerPoint, and we'll get on with the next topic of the day, which is inductance as a device. And this one, ignore the math because not responsible for this, but I want to talk through an idea here, and that's the transformer. You all have one, I'm sure, because that's how you charge up your iPhone or a calculator you might have a plug in the wall, an adapter. We're all used to those in our life. But I wonder if anybody's ever like taken that box that you plug into the wall apart and see what's inside of it. And I'll give Apple some amazing compliments because somehow they managed to miniaturize this. These things used to be like small bricks, and now they've become smaller and smaller and smaller. So it's a little cube. And what's happening is there's a first coil right here, which you plug to the alternating current, right? It comes out of the wall. And hopefully you know enough about what's coming out of the wall in all the buildings to realize that is not just a current that's going in one direction, it changes direction. So it goes both ways, and it does that pretty fast. It does it 60 times a second. Okay, and so while this diagram right here is showing the direction of the magnetic field, and if you use a little right-hand rule, you kind of have to be able to do this to do these problems. It's swirling around this way. My thumb points that way, so current swirling around this way. My thumb points to the right. That's why the magnetic field is shown going to the right. And of course, when it changes direction, current goes the other way. That makes a magnetic field to the left. And so the magnetic field in these coils caused by the current we're sending to coil 1 moves back and forth many, many times. Okay. I guess the result of that is that coil 2 here sees a change in magnetic field, and it has a cross-sectional area right here. So it sees a change in flux, and that change in flux is happening very rapidly over time. And so the rate of that change in flux induces an electromotive force proportional to the rate of change of flux. And the notation here is that's coil 2 because of the magnetic field, which is changing due to coil 1. And that's what we're talking about. This concept's called mutual inductance, and it is how transformers work. And we all live with them every day, and we just kind of take them for granted now. That's not any of that math or any of that discussion is not part of the course. Internet connections unstable. The thing I do want to talk about, though, because we will use it, is self-inductance. And so I just wanted you to think about this simple DC circuit and with a switch. And initially the switch is open, so there is no current flowing. And then so there's no magnetic field anywhere. And I'm showing with some little arcs here, this leg of the circuit, the current's going kind of up into the left. And so we have a rule that says, hey, that means that the magnetic field swirls around that piece of the wire, and it does the same thing over here, and over here the current's going that way. So I guess it goes under the bottom over the top here. And so in this area right here, if you think about it, everywhere is a magnetic field coming out of the page. Now, the problem with our mathematics on this is I don't have an equation that would allow me to calculate what the magnetic field is at all these locations. And I have no reason to think that it would be the same magnetic field. If it was a perfectly circular loop, okay, rather than a rectangular loop like we've drawn here, we have one equation that would allow us to calculate the magnetic field right at the very center there, would we? And that's the only point we can calculate. Since the magnetic field is changing everywhere over that area, it would be an integration in order to figure out, the flux. We're just not going to make you do it. But the point is, it's changing as soon as I shut that switch. Faraday's law says an electromotive force will be induced. Electromotive force will be induced so as to create a current which opposes the change. And so what would oppose that change? Induced. As soon as I shut this thing, because a magnetic field is created out of the page, there'll be a current that will try to swirl around this way through the loop, opposing the current which is created by the battery. I call that the induced current. And this is magnetic induction, induced current, I-induced, I-N-D. I need two I's there, don't I? Current induced. And you notice right-hand rule, that would create a magnetic field into the page opposing it, opposing the magnetic field which is created when I shut the switch. The result of that, and we're going to show this with more mathematics on Friday, is when I shut the switch right there, shut the switch, and I'm showing what current looks like over time, okay? The answer is, at the moment the switch shuts, the current does not just instantaneously jump up to some value, okay? In fact, and we'll show this on Friday, it must kind of increase slowly until eventually the battery overwhelms the current created by electromagnetic induction, by Faraday's law, by Lenz's law. Okay, the battery's going to win eventually. It's got much more energy available, but it is not possible to instantaneously jump up. All right, this idea is called self-inductance. The current in a loop creates a magnetic field in a loop which creates a current which opposes the current which creates it in the first place. It's almost hard to say that. Okay, it's maybe a little easier to see with these three diagrams. Okay, so I guess this would be follow just a little practice on right-hand rule. If the current is going around that way, creates a magnetic field to the left. Okay, and so if that current is increasing, that would be a magnetic field getting bigger to the left. So that's the direction of the magnetic field's change. There will be a current induced in the opposite direction to oppose that increase. So that's the change by the current increasing. There will be, and I always draw it smaller, a magnetic field induced in the opposite direction, okay, to oppose that change in flux. Okay, it's almost as if a little battery is created in this coil. That's the induced current, which is going that way to create this induced magnetic field to oppose the change in the magnetic field by increasing the current from the source at the very start. Interesting thing, on the other hand, and this is the good news, I guess, if you try to decrease the current, thereby decreasing the magnetic field. So if the magnetic field was this big, you decrease the current, it gets a little smaller. That's a change in the magnetic field that way. Okay, it's getting smaller. And so the Lenz's law and Faraday's law will try to create a magnetic field in the original direction as you decrease the current. It's almost as if a little battery is created right here, which causes current that way. And so self-induced electromotive forces in coils like this create little batteries that oppose change. The good news is, if you, as in the second case right here, if you have current in a circuit and you try to take the current away, you disconnect the battery, current will continue to flow until the magnetic field is completely gone, in which case it can't change anymore and it can't create any more current. Okay, and so that's kind of, I guess, the good news. And that tells you what these coils do in a circuit. It mitigates a loss of current, doesn't it? It keeps current going for a while on loss, so it's just not a complete break. Okay, here's some equations, and you are responsible for this. We've now kind of inferred that there's a third element we can put into a circuit. We started with capacitors a long time ago, and you remember capacitors, there's a constant that's involved in the capacitance of a device. It might have a dielectric constant, kappa, associated with it. Okay, there's a cross-sectional area and a length. And so the capacitance, the ability to store charge in a capacitor, was a function only of physical constants and dimensions of the capacitor. Okay, and then the next circuit element we talked about was a resistor. It also had a constant in nature, resistivity of a particular material. It had a dimension and a cross-sectional area, the length of the resistor and the cross-sectional area of the resistor. Again, resistance is only a function of a physical constant, the resistivity, and some dimensions of the material. And these coils, we have a symbol for that too, the symbol for self-inductance, which is like capacitance and resistance for a coil, for a loop of wires around a spool like this. The symbol is L, and we're going to see here in a second that it is only a function of a physical constant and the dimensions of the coil and parameters associated with building the coil. All right, so let's kind of go through this. We said that electromotive force is the rate of change of magnetic flux. Okay, and remember, this is in a single loop, one turn. In fact, most coils, like the one I showed you, I guess 2 weeks ago in the lab, have many thousands of turns on a spool, just like thread, okay? And so the overall electromotive force would be however many turns you have times the rate of change of flux in each of the loops. Well, let's try to get what that flux is. There was an equation when we talked about coils like this, that we used Ampere's law to find what's the magnetic field right in this area right here. what is B right there? And it's that equation. And so for that reason, I put it, oh, great, internet connection unstable, put it right there. And then of course, in order to get flux, I just multiply by the area. So that's the thing whose rate of change, that's the magnetic flux, whose rate of change gives me an electromotive force. Now, if you look at this, physical constant, remember what N was, and I wish physics books didn't do this. This was the actual number of turns divided by the length of the solenoid. And I specifically put that in right here, okay? A lot of physics books like to make the equation look a little shorter, so they use lowercase m for like 3,200 turns divided by this length right here. Because generally, as you're winding with a machine, that number is a constant as it goes around, okay? And so, but don't remember, that's always the actual number, 3,200 per length, per centimeter, or per meter in the MKS system. Anyway, I guess the point is, physical constant, constants that are associated with the dimensions and the construction of the device, a current, that could change, and the area, which is, of course, this cross-sectional area of any loop right here, okay? The only thing that can change right there is the current. Everything else are just dimensions and how many turns, things like that. And so this derivative right here can only act on the thing that's changing, and so I brought it outside. And everything that's left right here, that must be the thing we call the self-inductance. And so for a solenoid, for a coil, we have an equation like here at the bottom, and all I've done is I've taken these things in the parentheses right here, and I said, well, I've got N twice, don't I? I've got it in the magnetic field, and I have it in the magnetic flux, and so it's N squared. I've got a constant of nature, not the permittivity of free space, but the permeability for magnetism of free space. And I've only put air in this solenoid right here, the cross-sectional area of the coil and the length of the coil. So it meets the same criteria as we had for these other devices that we could connect to power supplies like batteries. Okay. Now,
Why are there two different equations for L? Like, what are the difference between the
yeah,
two?
I'm going to talk about this second one here. Okay, this is specifically for a coil, right? Well, we did talk about toroids, right? How would you find the magnetic, the induction, the self-inductance constant for magnetic induction for a toroid? For what would you find L? Okay, here's the way you go about that. I kind of backed out of this. Remember, this piece right here was magnetic field. And so let's keep the N. Let's back out mu0, number of turns per length, and I. And that is the magnetic field, but divided by the current. I just divided that current away right there because it's over here in the derivative, okay? And so that was something that could be done more generally, okay? And so that current's right there, bring it back out. I kept the area, okay, because that was in the flux, not in the magnetic field. And so if you're just looking for a general expression for the self-inductance for a device other than a solenoid, what you would need to do is take the number of turns of that device, take the magnetic field equation for that device, like you could for a toroid, divide the current out of that equation, okay, multiply by the cross-sectional area, and then that would be the self-inductance. And so all of this would be the right answer when you just don't know what the magnetic field is. It's not, you haven't defined what the thing is that's creating a magnetic field. Our best example is a toroid. And so all you would have to do then is substitute right here, magnetic field times area, using any magnetic field equation that we learned back when we were talking about sources of the magnetic field. Okay.
What happened to the negative sign
Yeah.
on the
Yeah.
coil?
Good question. Always a good question there. What when you're trying to decide that negative sign, I think I said last time, I ignore it. And it's a little sloppy, but what does that mean? What is the significance of that negative sign? It means Lenz's law is in effect. It means the current is going to flow. The polarity of the voltage is going to be such as to oppose the magnetic field change, the magnetic flux change, which creates it. And so in L is just a positive constant. That negative sign, I just ignore. If you want to put it right in here, you can. Okay, you can do that. But I get sloppy and I just ignore it. I always think of all of these as absolute values. And then we do what we're about to move into in a second here. We use Lenz's law and we decide, okay, what does that mean is going to be the direction that current is going to flow? What is going to be the direction of the change in the electromotive force? Is it going to be this way around the circuit, or is it going to be the other way around the circuit? And so a little sloppy there, good catch, but it's not an important negative sign. But if you want it right there, put it right back in. Okay. And to answer both those two questions, good to go. Again, seldom will you have to do this because I think we only have we have coils, right? Where that's the magnetic field. Let's see, what was the magnetic field around a toroid? I'm not even sure I have it memorized, but it was mu zero I. And I always remember, was it over 4 pi A? 4 pi R? I think it was 4 pi R, but I'd have to go look it up. It's not an equation I have memorized, but you can see I can take this right here, and when I divide the current away, like it's saying to do, multiplied by the cross-sectional area of the part of the donut where the magnetic field is, and I could come up with a slightly different equation for the self-inductance of a toroidal coil as opposed to a long straight one. I got to tell you, that's more for you future physics majors to think about, but that is why this equation exists. All right, self-inductance. I want to talk about units of self-inductance because that's always important. It's not too bad, I guess. That's a volt, right? Electromotive force, just a volt. This is a current. Why did I write current? How about amps? Coulomb per second, but let's go amp. Yeah, I can change a C into an A. There we go. Amps per second, right? And so apparently, if I'm trying to find what the units of L are, L must have units of volts divided by amps per second, which is what I wrote right there. Okay, well, a volt divided by an amp is just an ohm. So those guys right there are the units of an ohm. And then I've got a 1 over a second in the denominator. Anything that's in the denominator of the denominator is actually up in the numerator, right? Because you multiply by the reciprocal. And so an ohm second is a unit of this self-inductance, okay? And magnetism folks seem to like to rename constants like this. It's called a Henry, named after a scientist in the 1800s who did work on magnetism in coils. And so the abbreviation for the units of inductance is self-inductance is a Henry. Okay, and that's the deal. You know, what's the unit of a capacitance? We call it a farad. What's the unit of a resistance? It's an ohm. And now we have the unit of inductance, self-inductance, and it is a Henry. I do want to talk a little bit about energy in these coils because that is their function. If you think about it, what's the function of a capacitor? It stores charge, and because it stores charge, it is actually storing energy. And we said, well, okay, the energy in a capacitor looks something like 1/2, I guess, charge squared divided by that capacitance. And you could have gone 1/2 the capacitance times the potential difference squared. There's 3 equations, and you had to use one of them on the second midterm. So hopefully you know what I'm talking about there. That's the function of a capacitor. It stores energy as charge. It seems to me that an inductor is storing energy as well in that magnetic field, okay? But it's storing energy as a current and the magnetic field that the current creates. And so unfortunately, I can't talk about a fixed amount of energy like I can in a capacitor. You can charge up a capacitor, disconnect it from the circuit. As long as it still maintains that charge, it's like a little battery almost that has that charge ready to dissipate when you hook it back up. You take an inductor out of a circuit and it no longer has current running through it, instantly the magnetic field goes away. You can't maintain it that way. And so you can't talk about an amount of joules, but you can talk about the rate at which energy is either saved in the inductor or released from the inductor as long as current is moving from some other source. And of course, our equation for power was V times I. You could also have, I guess, I squared R. And I guess you can also have V squared over R. All of those were possible alternatives to this because you just apply Ohm's law somewhere and it works out for you. And I think we said the electromotive force the voltage in an inductor was just this self-inductance times the rate of change of current. Okay, so let's see. That must mean, since this is the rate of change of energy in time, I guess these guys cancel. And if I do want to find that energy, that kind of unit of energy, while the inductor is connected to a circuit and current is moving in it, okay, I would just integrate both sides, right? And so L is just a constant. And so to get the total energy, I'm just doing the integral of L I di. And this is just what's the integral of x dx? The answer is x squared over 2. So the integral of I di is I squared over 2. And so while that inductor is in the circuit getting current, that would be the energy that it's storing. Okay, and you could compare that to the energy I was talking about for a capacitor. Difference, of course, is I can walk a capacitor out of a circuit. It still has its energy as long as it maintains its charge. As soon as I disconnect an inductor, it loses its current and away that energy goes. But it is there to be used while that's going away. All right, energy in a coil. I think just to be consistent with what we did with capacitors, like to sometimes think about not the total energy, but how about the energy density, the energy per volume? And of course, that's what Apple has done so successfully. They've taken that energy density with that little cube and made it as high as it can possibly be. That's why sometimes they get a little warm on you if you keep them plugged in for a while. And so I guess I'm going to recall what self-inductance was for a coil. I's cancel here, right? And so that kind of goes away. And so those are the numbers I put in. That's exactly what I had a couple slides back for self-inductance. So that's 1/2 self-inductance. And then current squared, what I did here is I took the magnetic field in a coil and I divided it by the pieces that leave me with current, and I squared that. And if you do that, what you find is you get a cross-sectional area and a length. That's just the volume. And I get a whole bunch of constants left over. Let's see, I got that guy and I got that guy. Okay, let's see what cancels. That squared cancels both of those. Okay, this is mu0 squared, right? So it cancels one of them. That's why this is only to the first power, not squared. And then I've got a length squared here divided by a length. That's why I have a length to the first power. And so I've got the magnetic field squared. And so it looks like the energy density, dividing the volume over to the other side, getting rid of that right there. The energy density, lowercase u, would just be 1/2 mu naught times the magnetic field squared. The only reason I give you that is we talked about energy density in a capacitor. It looked very similar, okay? Only it was the permittivity of free space and an electric field squared in the case of a capacitor. But you know, why we can't put these constants in the same place, why one's in the numerator, one's in the denominator, is an interesting question that I can't answer. But the fact is, the energy density in one of these devices is directly proportional to the magnetic field in the case of an inductor, or the electric field in the case of a capacitor squared. Energy density. All right. On Monday, we'll come back and we'll build circuits like this. So I'm going to cut this off in just a second, but you can see, hey, let's say I close a switch here. I got a battery, a resistor, and a coil. As I said, this is how the current is going to increase. And I'll show that when we come back on Monday. All right, I want to jump out of this, stop sharing this, go over to the other PowerPoint, and we're going to pay attention to that negative sign for just a bit. I'm going to share with you, hopefully, I got to switch over. Let me close that guy. Nope, I want to discard my annotations on this and switch over to another PowerPoint so we can do the iClicker here. All right, let's go to magnetic forces. Got it. Okay, reshare that with you. Magnetic forces. Yep, there it is. And I have to bring it, okay, I have to bring it over to here so that you'll see it when I start the iClicker. All right, let me back up a couple. I want to start, we did that one last time. So let's start with this one. All right, your screen sharing is paused. Resume share. Okay, there we go. Hopefully you can see a slide here. Let me make this get a little smaller for you. And yeah, that looks okay. And you can see I've got a bar magnet here. There's the North Pole. I have a loop of wire and a resistor. Okay. And so the question, I guess, is as I move that bar magnet closer to that loop of wire, which way is the current going to flow in the resistor? And I think I can go start. All right, mine's changing. Okay, there we go. All right. And so your questions, of course, are the current is either going to go, I got to get my annotate button. It's either going to go from A to B, it's going to go from B to A, or you can decide that because of this, you're not moving the loop, there's no current. So go ahead and put your answer in. And we'll try to get my annotate. There it is. I got my annotate thing. Draw. Yeah, good. All right. Yeah, we've got 9 folks in. It'd be like, who wants to be a millionaire here? Let's phone a friend. Yeah, the majority seems to think A. Let's put that away. All right. Let's see how many people are here. We got 13. That's probably about it. So I can stop it right there. And I think I'm going with the majority here. That's what I think too. Close that. If you think about it, what is happening as I move this magnet closer to this loop? I think I've got a magnetic field there. And as I move it in, that magnetic field gets even bigger and bigger. That's why I drew a longer line. That's the direction of the change in magnetic field then. Lenz's law says the current is going to flow so as to oppose that. Opposing that would be that way. In order to create a magnetic field, I always refer to that as the induced magnetic field. The opposing magnetic field is that way. To create that magnetic field, current will need to go around this loop of wire this way. Okay, and so the current will go from A to B when you finally get over the resistor. So I agree with the majority on that one right there. Okay, let's move on to the next one. I gotta go to the mouse here. Boom, comma, there we go. And let's erase my, clear my drawings. There we go. Okay, so I made this one a little smaller. I've got some things I should be able to show you on this one, hopefully. And so the switch is closed. What's the direction of the current in this little ring right here? And you have 2 choices. You have figure A, it's either going to go around that direction. It was hard to describe that as clockwise or counterclockwise since the ring is sort of perpendicular to the page here. So I went with figure A or figure B, or A then B, B then A, or no current at all. Okay, so those are your choices, and go ahead. Close that, and you got to kind of pay attention to the direction of the magnetic field, don't you? And you got to pay attention to the direction of the polarity of the battery. Current's going to go that way, isn't it? All right, got about 7 in. Kind of split between A and B here. All right, think about what the direction of the magnetic field is when you shut that switch. Current's going around that way. A couple people still thinking here. All right, doesn't look like we're getting any more, so I'm going to cut it off right here. And I'll show you what most people have. A few more people think B than A. We'll close that up. I have a little hidden figure here, okay? And hopefully you believe See what's happening right here once I shut the switch? Current goes around this way. I would have swirled my fingers around and I would have said there's a magnetic field to the left. And that's, I think, what's being shown right there. There's a whole bunch of arrows going to the left. Okay, so in that loop then, no magnetic field, then a magnetic field to the left. Opposing that would be a magnetic field to the right. And so which of these is the magnetic field going to the right? That's figure B. And so I think figure B is the right answer. So slight majority view there, pick B, and I'm with you on it. I think B is the right answer. Initially, the change is that way. The loop creates a magnetic field in the opposite direction. In order to get the current going in the opposite direction, figure B looks like it's the right answer. Any questions on that one? I had another figure in here too. I was trying to see what. Yeah, don't worry about that. Okay, so we're good to go there. And one of the things you'll. Yeah, we're going to B. All right, one of the things you'll notice, I guess, is you have to visualize these fields around these loops. And so you have to have your right-hand rule in effect and clearly in your mind in order to work through these pictures. All right, this is similar to one we did. I guess I just changed the direction of the way the bar is moving. Now the bar is moving to the left. Magnetic field is into the page. Flux is getting smaller because area is getting smaller here. So flux is getting smaller because the area is getting smaller. Here's your first hint. You got to oppose that with a magnetic field induced out of the page, right? And so how would what current would flow to create a magnetic field out of the page? Let's see what people think. And we're kind of split, clockwise or counterclockwise. It's one of those two, isn't it? All right, we're in with 10, so we'll stop here after about a minute. And so magnetic flux is getting smaller and the magnetic field is into the page. The way to counteract that with a smaller area is to increase the magnetic field out of the page. In order to get a magnetic field out of the page, current would have to move that way, wouldn't it? So I would say counterclockwise. And again, I think a few more people said B, one or two more people said B than C.
I thought if the field was decreasing, then the induced field is the same way.
Yeah, hang on, let me think about that.
That's what I thought as well.
Oh yeah, no, you guys are right. You're onto it. I said exactly the wrong thing. Yeah, no, I drew you want that, right? And so you want that way. Oh, you're on to me. Good work. Yeah, I'm going to go exactly with what you said. Everybody hear what they said, because what I said was wrong. Yeah, they're saying the area is decreasing, right? So you got to make an induced field into the page. Absolutely true. Absolutely true. And so in order to make that, the current has to go that way. So now I'm going to erase what's wrong here, and I should go clockwise. All right. Apparently, I should have answers on these things for myself, so I don't make silly mistakes like that early on a Friday morning. And I want that one. All right. Good catch. Thank you. Appreciate you correcting me. All right. Let's move on to the next one. All right. This time, erase my markings here. Clear my drawings. This time it's the South Pole moving towards that same loop that we had just a second ago. I've asked one more question, A minus B or B minus A, which is equivalent to which way is the current flowing, right? And remember, near the south pole of a magnet, that's the direction of the magnetic field. And as you move the south pole towards the loop, this thing is getting bigger in that direction. You got to be able to visualize what the magnetic field around a magnet looks like. So that must be the induced magnetic field. And that's enough hints. So we'll cut it off, see how people voted. Slightly more people said B. Let's see if I agree or if I make a mistake again. All right, so let's see. If the magnetic field is increasing that way as the magnet gets closer, because the magnetic field around a bar magnet does something like this. So it's going towards the south pole and then all the way through. That's getting bigger. The induced magnetic field is in the opposite direction. In order to create a current, a magnetic field in that direction, I would need current to run around the loop that way. That would create a magnetic field in that direction. So when it comes over to here, it would go from B to A. Current would run that way through the resistor. And so I guess B must be higher than A in potential. And so VA minus VB would have to be a negative number. Okay, or negative value, because B has to have a higher potential if current is going that way. All right, questions on that? I get this one good? Didn't mess up this time? Excellent. Let's move on to the next one. We'll do one or two more. I'll hang around if you have to leave and you can't stay to do all these. I'll hang around and do a couple more for everybody who's willing to stay. But I do see it's 10:22, so if you got to move, that's all right. If you got to go on to another class or something. All right, so this time I'm moving North Pole. I basically reoriented that loop, haven't I? Just changed the orientation, but it's the same problem. A North Pole is moving closer to a loop. The loop is sort of perpendicular to the plane of our paper here. So go ahead with that one. Click. That's your first hint. North pole of a magnet, magnetic field. All right, I think I'm going to cut it off here. I see there's only 9 people still around, so other people may have to leave. Got 6 in. Okay, so that's the first step. North pole moving that way creates a magnetic field, which is getting bigger in that direction. Opposing it, the induced magnetic field is in the opposite direction. Okay, in order to get a magnetic field that way, current has to go this way around that loop. Okay, and if it goes that way, current must move from A to B. So that must be my answer. All right, moving on. Next one here. This one, be careful about, and just it's somewhat visualizing what's in the paper. Let's start this one. And so now the magnetic field is moving this way. And a bunch of people jumping right in, I think. Let's see if they're jumping in the right way. Be careful now. Are these magnetic field lines going through the area of that loop? In fact, what is the flux? All right, why is it not telling me anything? I'm going to stop that. Okay, 6 people are in, and I think the answer is the flux is 0. So even if you move it, there's no change in flux, it stays 0. So with this orientation of the magnetic field in the plane of the paper and the loop in the plane of the paper, it's got to be 0. There's 24 after. Let's do one more, maybe 2. This one's kind of an interesting question. Okay, see what we're doing to the magnetic field here? We've got a north pole right now, and we're pivoting it about that point and bringing the south pole in. So think about your change in flux now. I'm going to stop and restart here. You're still answering for the previous problem. So go ahead and re-enter if you have to. Draw a few little hints. Starts this way. When the South Pole brings around, that's B2, I guess, once the South Pole gets there. That's the change. That's B induced. Induced B. All right, I'm going to call it quits on this one. So here are my markings. Initially, when the North Pole, maybe I should call that magnetic field when the North Pole is near, is that way. When the South Pole comes around, call this B south, it reverses direction. It means the change in the magnetic field is to the right. A magnetic field will be induced by current moving around, then to the left, because left opposes right. Okay, and so let's see. That would mean that the current has to flow around in the direction of these arrows right here. Okay, so that means it'll come here, go from B to A as it's turning right now. But think about what happens when it rotates again. Current should change direction, go back from A to B. And it'll keep doing that as the North and the South Pole flip. But initially, when it does this, it moves from B to A. But as it keeps going and it comes back to the North Pole, current will reverse direction, go from A to B. I think I got to quit right now. And so I'll stop sharing this with you. Those of you that hung around, I will be doing office hours, I think around 1:30 again. That time seemed to work. For any questions on any of the worksheets, we can go through more of these at that time. But you guys have a great day and a great weekend if I don't see you later on. Questions? All right, then I'm ending it.